Welcome back to the classroom. My name is Mr. Wong. So our previous recording, we talked about circular motion on a string. This lesson, we're actually going to focus on doing some calculation questions on those problems. So let's begin and let's see how many we can do. Okay, so our first question we're looking at. Okay, so now we're going to go into our first question, which we are playing totem tennis. The ball has a mass of 150 grams and is swinging freely around a horizontal circular path. The chord is 1.5 meters long and it has an angle of 60 degrees to the vertical. So it says calculate the radius of the ball's circular path, determine the net force that is acting on the ball at this particular point, and calculate the size of the tension force. So diagram is drawn for you nicely here, but I'm going to skip to a blank page where I can draw the diagram again, just so everyone knows how to try and draw the diagram. So it says an angle of 60 degrees to the vertical. So if I just draw a vertical line, dotted along like so, 60 degrees from the vertical means this, okay? And then we have a mass that is 150 grams. It has a gravitational force pulling it down. The chord is 1.5 meters long, so it's looking like that. Okay, that's what we have there. All right, the first question is, what is this radius component? Well, we can actually use simple trigonometry to work that out. So we can actually use sine theta. We have the opposite side, which is r. We have the hypotenuse, which is 1.5. Theta is 60 degrees, so I'm going to change that to 60. So sine 60, change it around. R is 1.5 times sine 60. That gives us an answer of about 1.3 meters. B, it says determine the net force. So net force is, and I'll do it in a separate type of color, net force is going in like this. Okay, we have the gravitational force, which is aligned in this component. So what you can actually see here is we can actually use tan theta. Our opposite side is the net force over the gravitational force. So if I do my substitution of values, this is what I end up getting. Gravitational force is mg, so 0.15. Remember, that's because this is in grams, times 9.8. So readjust that formula over. So tan 60 times this value that we have down here, we get a value of about 2.55 to our center point here, okay? And then our last question is question C, and it says calculate the size of our tension force. So we want to find this part here. So you can use this, you can use the gravitational force, you could use the net force, whichever one you like, and it'll give you the exact same idea. So we can use our net force. Okay, so sine theta is equal to our net force divided by our tension force. So it's sine 60, tension force is what we're trying to find, net force is what we already have, that's 2.2 or 2.55. So 2.55. If I readjust my equation around, it looks something like this, 2.55 over sine 60. And that gives you a value of approximately 2.94 newtons going in that direction up. So that's our first question there for mass on string circular motion. Let's try another question. Okay, so this will be our second example. And it says we have a 250 gram glider at the end of string swung horizontally. Now, if it's, I'll say that again, if it's swung horizontally, it's being spinning around like this. So we don't need to consider the changes in the forces, the tension and all that. What is the speed of the glider? What is the horizontal component of the tension force? What must the tension in the string be when the glider is at the bottom of its path if it's a vertical motion? So 3 questions here. Let's go with A. What is the speed of our glider? We have mass, we have radius, and we have time. Okay, so we can actually use what this one is looking for the linear velocity. Okay, so linear velocity is 2 pi r over t. 2 pi r, radius is 1.2 over t, which is 2 seconds. That's how long it took for 1 revolution. And so we get a speed of approximately 3.77 meters per second. For question B, what is the horizontal component of the tension force? Okay, so if I redraw this string to look a little bit easier to see. Okay, the horizontal component of my tension force is also my net force as well. So what I can actually do is I can actually find the gravitational force and the angle. Oh wait, I don't have the angle. Okay, so that's all right too, because I know that the net force is the contributing factor of my centripetal force. So if I just use my centripetal force formula, I can still find the horizontal component of my tension force. So our horizontal component of the tension force is equal to the gravitational force, or not the gravitational force, centripetal force, which is mv squared over r. So that will be 0.25 to represent the 250 grams times velocity, which is 3.77 square, divided by our radius, which is 1.2, and that gives us a value of about 2.96 newtons going towards the center point there. All right. Last one is, if the glider was swung vertically, what must the tension be when the glider is at the bottom of the path? So at the bottom of the path, let's just redraw our diagram. As you can see, there's quite a lot of different scenarios in this question, which makes it really nice to try out. So we're spinning it up around like so. So at this bottom point here, the net force is our centripetal force, but we have to counteract. The net force is a counteract of our tension, which is going up, subtracted by our gravitational force going down. Or you could say it's adding with our gravitational force, but do take into account this is going to be a negative value because gravitational force is going down this way, tension force is going up that way. So up to you how you would like to display those numbers, but you know, that's the way to demonstrate. Okay, so we'll have the centripetal force is equal to our tension force subtracted by our gravitational force. If I just expand my equation now, that's what I have here. Okay, I want to find tension force. So this is what I get here. Okay, now I can do the substitutions. I might need a bit more space, so I'm just going to rub out what I wrote for A and B here. just so I have a bit more space to do some of the working out. This is what happens when you design slides that weren't supposed to be written on. You run out of space very quickly. So let's do our substitution. 0.25 times velocity, which was 3.77 square. Was that? Whoops. Already found the centrifugal force in question B, so I won't need to do that calculation again. So that was 2.96 equals to tension force subtracted by our mass times gravitational acceleration. Now, see how I put the negative here? So if I already counted for that vector, I'm not going to bother doing that again. Just going to leave it as it is here. So our tension force is going to be equal to 2.96 plus the 25 times 0.25 times the 9.8. So we get a tension force of about 5.42 newtons dragging it up. Okay, so that's how you do this second question here on our calculations. All right, so a challenge for everyone here is to have a go at this HSC physics question from 1995. There will be a video link uploaded to guide you through how to do this video or this question. If you found this video useful, give it a like and subscribe if you haven't done so already. Thank you for listening up until now. There is one additional bonus question that I will explore, but that will be a separate video in itself again, so stay tuned. But for those who want to try this question, please have a look at the next video